Hi everyone, I hope everyone is keeping safe out there and is enjoying the class so far. This week we're going to get into some really exciting stuff, and that's about perturbations. So when you start to make a movement or when you're performing a movement, typically you're not expecting anything to disturb what you're doing. But what happens in real life is often that we get these perturbations, and these could be visual or mechanical. And we actually have to either figure out how to work with that perturbation or correct our movements. And so the concept that we're going to focus on in this week is that how do these perturbations provide a window into voluntary control processes, and how do we use feedback in order to actually achieve our goals in light of these perturbations. So we got to come back to our feedback loop, right? And so this is the optimal feedback control policy. And what it actually does is it's actually going to convert state variables, like for example, our state estimation based upon sensory feedback and the feed forward efference copy. And this optimal state information is going to actually come back and feed into our optimal control policy. Right? This is an estimation. Based on the estimation, what movement are we, or motor program are we going to make? And therefore, what motor commands are we going to send down into the muscles, right? And so what changes in this model, what we're starting to see, is this green box here, which is the task selection. And the task selection specifies the goal of the behavior, right? Which then actually defines the corresponding control policy. And so what this green box says is that we have the goal of the task is really going to have a significant effect on the control policy that we're actually going to instantiate. Okay? And so one key feature of this optimal feedback control is that errors, by virtue of the efference copy and the sensory feedback, are only going to be corrected if they affect the behavioral goal. Otherwise, just kind of keep going with that motor program. And in addition to the role of the neocortex in correcting these errors is spinal feedback. Okay, spinal feedback, which means at the level of the spinal cord or the brainstem and doesn't require neural control. And these spinal feedback processes are a lot shorter in time, so they occur a lot faster. And a key feedback of this spinal feedback is that it's kind of important for cyclic behaviors such as walking and locomotion, but it doesn't appear to be ultra useful for voluntary control of discrete movements. Kicking a ball, hitting someone in the face, all these kind of things. And so when we look at perturbation paradigms, we can look at it in two ways. I'm going to show you some first of the upper limb. So the upper limb, we can actually look at the adaptive responses of humans in a couple of ways. So the first way that we can do it is by, if we look at somebody doing a workspace, with a planar robot, so just in the X and the Y dimension, and they have to make movements from a start position to a target, what we can do is we can do a mechanical perturbation. So for example, because the robot has a motor in it, you can actually drive these perturbation forces through the handle that the person is holding. These kind of perturbations, we could do a force field. So as they're making movements in a straight line, it's actually going to push them out. And this depends upon the velocity. So the greater the speed that they're moving, the more the perturbation, the more the force field pushes them outwards. And of course, it could be directional dependent. You could also have a step force, which is, as you can see here, is just basically as you're moving, it's going to push you out by 12 newtons, right? So whatever force you are applying on the handle, it's going to add 12 newtons of force. So it's going to push you outwards. And we see how people actually start to adapt to these force fields. Another way to do it is by doing a visual perturbation. So let me show you what that means. So what we have is the start position and the target, yes, and you're supposed to make these straight arm movements. But in order to get you've got a difference between what you see visually by the cursor, the straight line in red, versus what the hand has to do to get to it. So in this case here, in order for the cursor to go from the start position in a straight line to the target, your hand actually has to move on a 45-degree angle. So it's very much similar to if you are trying to use a mouse, but you are facing upside down, right, from the screen. It's really hard to do that visual motor translation. So this is very much in the same thing. Another way that you can do it is, with respect for reaching and grasping, is to manipulate the size of the task. So in this case here, you've got these two objects, a small object, and then you can make it a large object by having a ring on it. And as people are actually reaching for the object, what you can do is suddenly change it from a small to a large, because this ring will pop up, or conversely from a large to a small as they're reaching by dropping off this ring. Okay, so you can manipulate the size. And we know that size influences our maximum grip aperture, our trajectories, right, all these kind of things. Another thing we can do is manipulate the location of the target. So for example, people are told to, these are three objects and they each have a light in them. And you're told when the light, reach for the target when the light goes on. And so for example, if the light in the middle goes on at the start, as you're starting to reach for it, suddenly the light goes off and this new one comes on. And so you're supposed to make a corrective movement and reach for this one, right? So you've got to change your movement goal from initially reaching for the middle target to reaching for this leftward target. So those are common perturbation paradigms in the upper limb. Of course, in the lower limb, it's a little bit different. So in the lower limb, what you can do is use this, what's called a split belt treadmill. In this case here, you're walking along, and the belt direction, is moving in its typical fashion like this. And then all of a sudden, the belt, which is underneath the left leg, switches direction, right? So it kind of makes you do the slip motion with the left leg. That's one way to introduce a perturbation in gait. Another way to do it is when they're on a treadmill like this, and this is really complicated, I know, but basically you put this harness around the waist, and the harness is attached to all of these cables that work through a pulley system and have motors. And so what you can do is, as they're walking along, one or more of these motors can actually be active, which would actually pull you in a certain direction. Okay, so that's another way to do it. When we're talking about walking, what we can do is have them stand on a forced platform like this, in a harness, because we don't want them to fall over, and they're attached by this waist to this pusher. And then as they're standing there with their eyes open or eyes closed or doing a particular task, the pusher actually produces a perturbation, in this case in the X direction. So it pushes them forward, and we see via the data collected on the force plate their center of pressure and how that changes. Okay. Another thing that you can do is using a sensory apparatus. They have one of these at San Diego State University, and what you do is you're just standing there on this platform and in this kind of structure like this. And what can happen is one of four things. Is as you're standing there, the structure actually moves backwards. And so what happens is people actually respond to that by also moving forwards, right? So this is when you actually change the vision reference. The second thing you can do is you can actually keep the structure there, but you suddenly tilt the platform, and you see how people respond to it, right? So both of these are changes in movement moving forward, but one is actually done with vision, and the other one is actually done with the support, okay? So this is with eyes open. What you could also do is just tilt the platform when the eyes are closed. And of course you can tilt the platform forward as well as move the reference support together. And again, you're seeing how do people respond to these perturbations. And of course, we look at this in neurologically healthy populations, and then we look at how this changes depending upon age or neurological status. Okay. So in the first slide, where we talked about the optimal feedback control system, I talked about feedback that's provided at the spinal levels. So although I typically talk a lot about the brain, right, and how the brain controls our voluntary movements, what we also know is there's control at the level of the spinal cord. All right, I talked about this in gait. And so muscle activity that's associated with feedback corrections to mechanical perturbations especially can actually have rapid motor responses. And these responses can be either short latency, which means you actually get a response within 20 to 45 milliseconds, which is really short, okay? Or they can be long latency responses in the order of 45 milliseconds to 105 milliseconds, okay? Which means it takes a lot longer, of course. And there's a difference between these two, and we derive these on the basis of time. So the first one, the short latency response, is actually generated at the level of the spinal cord, okay? The size is relatively small, so there's only a small amount of response or adaptive response to the perturbation that can occur. And it can only actually be modified over days and weeks of training. So if I keep putting you on the small perturbation training program, we don't see changes from trial to trial or from session to session. We actually see this modification over days and weeks, so it takes a lot longer. Okay. In contrast, these long latency responses actually include a transcortical feedback pathway, which means that we have to, because it crosses over, so it crosses over and then it goes to the cortical system or the motor cortex as well as the sensory cortex here. And these long latency responses can be modified by changes in task instruction, stability, and also in terms of joint dynamics. So there's a big difference there, right? The long latency responses are under voluntary control because we use our neocortex and is open for modification even on a trial by trial basis. Whereas the short latency responses, because they're generated at the level of the spinal cord, can't actually be modified by our conscious wishes, right? It's very much like a reflex, right? They cannot be changed just by thinking. So just keep those in mind as we move forward and we start to look at how long these responses to mechanical and visual perturbations take. So the first work I want to talk about is in reaching and grasping, and this was originally done by Castello and his colleagues in 1993. And what they actually did was they had people reaching from a start position to cylinders, and the cylinder was either small or large. And then what they had control trials where you're asked to reach to a small target or reach to a large target, and that provides us with that control data on which we can say this is what normal, quote unquote, normal behavior looks like, right? And then they have these perturbed trials, right, where you could actually have people start to reach for a the small cylinder, and then suddenly they have to reach for the large cylinder, or vice versa. They initially think they're supposed to reach for the large cylinder, but then, by visual turning a light on, they actually have to change and reach for the small cylinder. So here on this graph, I'm showing you wrist acceleration in this, what's called the unconstrained condition. Unconstrained condition means that they weren't told what kind of grasp that they wanted to use. They could have used a precision grasp. They could have used a power grasp. And what you can see here is look at the control trials in this dark, in this light black, if you will. So this is acceleration, right, which is the derivative of velocity. So we get to see this control trial in the gray actually shows us what the velocity would look like as they're reaching. And it kind of works like this. A velocity profile would actually be like this over the whole time period, right? And it would be centered here. And we would have the speeding up and we would have the slowing down portion. Well, velocity, because it, looks at the change in speed over time, within the accelerative portion, we get movement like this. And then here's the decelerative portion. And that's exactly what we expect to see for velocity in typical reaching. Okay. So look at the control. We see that we get the peak, we get a difference in when they reach the peak acceleration of about 38 milliseconds. So in the perturbed, it actually occurs earlier. And then on the decelerative portion, it is actually at about, you get this 60 millisecond, change in when we actually see the peak deceleration, if you will. Now, let's have a look when they were told just to use a precision grip, right? And so what happens is when they're using a precision grip, we see that they're time locked with respect to when peak acceleration occurs. Doesn't seem to be much of a difference. Also look to see the amplitude looks, pretty much the same. But what we see is they're also locked here in deceleration. So they reach peak acceleration and peak deceleration at the same time. But the actual movement time takes a lot longer for the perturbed trial. It takes about 100 milliseconds longer to complete the movement than it does for the control trial. And what you see is it's really, this lengthening occurs at the end of the movement. Yes? So it's not a complete elongation of the movement totally. It's just limited to this final grasping component, right? So that's wonderful. What we can also see is when we look at the grip size. So actually looking what's going on at the fingers, right? And this is, we're looking just at the precision grip. What we can see is that the grip size changes. We get some people who actually use a strategy where they maintain that same kind of perfect grip shape, what we call the single grip. But we have people in those perturbed conditions, subject TM, who actually starts to open the hand, right? And then when the light comes on telling you that you now have to reach for a different size cylinder, they actually reform the grip. So what they do is they start to close the hand and then they reopen it again, okay? So here, this person with the single grip is maintaining or slightly adjusting the motor program, whereas subject TM with the double grip is actually, what are they doing? Are they changing it, right? Are they actually using a new motor program based on the size of the object? Interesting. And what we see is, let's look at the grip velocity, right? So in the single grip, which is, we're going to use that as our control, right? We see that velocity increases and then really decreases when they go to grasp the object. But when we look at the double grip, we get this initial acceleration here, which is time locked with this first grip aperture formation. And then we actually see the grip velocity, because they now have a shorter amount of time by which to make that precision grip based on the object size. And you can see that the amplitude, how fast they're making that grip, actually is a lot quicker. And so what we can see here in the study from Castello is that the adaptive response to the perturbation is actually a rapid change to another distal pattern. And what we see is in most individuals, this is achieved by an early adjustment, both here and here, to the kinematic organization of both the, what we call the the transportation phase here, so when you're moving towards it. But the fact that we get this here is actually showing us that the manipulation, where we're actually forming our fingers, is actually going to be affected, yeah? When we move this a step forward, we can actually look to see what happens, not just when we perturb the target, the size of the target, in this case of Castello looking at the shape of the cylinder, but what happens if we actually move it with respect to where you're supposed to be reaching. And so what I'm showing you here is this device here is called the KinArm, and it was actually developed by a Canadian group at the University of Toronto. They use it for stroke rehabilitation. I'm not a fan of it. Look at it. It's massive, it's bulky. Basically, you're limited to, elbow flexion and extension, which is a really, if you think about everyday life, how does that help you with rehabilitation, right? And so anyway, let's have a look at what they did. So what they're looking at here is these long latency motor responses, so the transcortical responses, okay, when you actually change both the goal and the location. And so in this task, I'll show you the perturbed. They have two conditions. One is the circle condition and one is the bar condition. And they're told to just reach for these from their start positions. So in the circle condition, in the unperturbed, you can see that they can make these movements in basically straight line trajectories, just like you and I would, right? And with the bar, very similar. They reach straight for it. Boom, boom, boom. Okay. However, when you actually perturb them mechanically, okay, so they're actually going to drive the arm outwards with using the motors that are up here, what happens is that people start to come out, right? They're like, whoa, perturbation, boom, and then they come back in. This is the correction here, okay? This is where we're seeing the corrective movement. With the bar, what you can see is, though, because, the target is a lot less defined, there's more room, they don't actually really correct for it, right? You don't see that, you don't see this return system as much. And that's basically because they can still achieve their goal while being perturbed, whereas to achieve the goal of the circle, they need to make a corrective response. Now let's have a look at the hand corrections, only in the perturbed conditions, of course, for the circle and the bar. Now, let's note here that the legend is a little different. The circle is in blue in both of these, and the bar condition is in red. So if we look at the hand corrections with respect to position, we can see that the arm drives out, right, and then it comes back to the 0 position because it's a straight line in the X dimension, right? We don't want that movement. Whereas in the bar condition, they actually allow it to move. They keep going, and then they just keep moving in this X position, right? As you can see here, this is the X. You see them moving outwards. Here's a hand correction. They're also moving outwards. So they're actually not making a hand correction in this bar condition. And then what we can see here is that the elbow flexor of the EMG, we don't actually get much with the bar condition, but in the circle condition, that brachioradialis, which is an elbow flexor, right, coming inwards like a bicep curl, we get a lot of activation. And this here shows us at about 50 milliseconds after the perturbation, right, we start to see this ramping up of the elbow flexor EMG. This would correspond to, this is 50 milliseconds in time, and them actually using the elbow flexor to come back in to hit the target, okay? And so, again, I would say from this study is that the long latency motor responses consider the spatial properties of the goal, right? So the smaller target of the circle, whereas the bar is a lot longer. And so by using this information, the brain goes, I can achieve the goal of the bar condition without having to make a corrective response, as shown by these reds. But in the circle condition, as they're being perturbed, the neocortex goes, whoa, if I want to reach this goal, I have to make a hand correction and I have to actually use my brachioradialis, right, in order to get my arm to come back inwards. And again, what we can see is that the movement of the elbow flexor starts at about 50 milliseconds after the perturbation, okay? So it happens pretty quickly. So another way to do it is not actually just to push the arm outwards, but it's actually to apply what we call a Coriolis force. Now, Coriolis forces are actually proportional to limb velocity, which basically means the faster your velocity, right, the more the force is going to push you outwards. So if you move really slowly, your arm is only going to be pushed out a little bit. But if you're moving fast, like whoom, what's going to happen is it's really going to push you, it's going to push you outwards a lot more. So if I am to show you the formula for the Coriolis force, the Coriolis force denoted by F sub core is equal to minus 2 times the mass of the arm, right, times the angular velocity of the rotating environment times the linear velocity of the arm, okay? So in the case of when you're using a planar robot such as the H-Man or something as we see that looks like this, right? So it's just a planar robot and the body is staying still. There's no movement of the arm at all. We can actually remove this component here, right? Because the environment isn't moving. So in this case, we can basically say, what's the mass of the arm? Which is it's a known constant for each person. What is the linear velocity of the arm? How fast is it going? And basically, based on the velocity of the arm, apply a force that is minus 2 times the mass of the arm. Boom. Okay? And that's basically how it works, right? And so this means, again, here's a really important thing if we put it in natural language, is that there's not going to be a Coriolis force that acts at the beginning, at the end of the movement, because there's no velocity, right, or very little velocity, but the motion of the Coriolis force is actually orthogonal, moving, which means moving outwards, and proportional to the velocity that is generated. So that's why we see this kind of Coriolis force that acts in this way. So in most places, we actually apply these Coriolis forces using a robot. But there's a special place in Brandless University called the Ashton Graybill Spatial Orientation Laboratory, where they have created an entire room that can generate Coriolis forces. And they use this to look, it's a massive room, and they use this to look at how people actually walk, how they move their arms and their limbs. They can actually put people in these kind of astronaut states to look at how do people move in different perturbation forces. And of course, when people are just sitting there, how does that change? And so in this case of here, this person sitting here, the room is going to move around you, and we look to see what happens to head movement, okay? And you can manipulate so many things, the acceleration of the gravity, the centripetal acceleration, of course, the Coriolis acceleration, and the tangential velocity. So it's really great. And this is kind of what the room looks like as you would walk in, and you can see it. So it's actually got the small space within it, and this is going to rotate around and around and around. Okay, so here's a person sitting in a chair, probably going to do an arm movement. So Dizio and Lackner, who really kind of just started this whole work on Coriolis forces, they're genii, if you will. What they looked at was using this Coriolis force to look at how people adapt to perturbations. And so they use this paradigm, which we get the pre-rotation. It consists of 3 phases. Pre-rotation, which is just like your baseline data, looking to see how people make these movements. Then you put them in the rotation, okay, and to see how behavior changes. And then what you do is you take away the rotation again, right? So you see whether they can adapt back to the pre-rotation state. So what we've got here is error in terms of millimeters, and it's directional, right? So it is a vector, it's a vector component. And so 0 here, you can see in the pre-rotation, people make really easy movements, very little endpoint error, right? So on the order of 20 milliseconds, which is 2 centimeters, right? And then what they do is at trial 41, they unexpectedly actually put this rotation in the movement. And what you can actually see is, look at it, your endpoint error actually increases dramatically up to 40 millimeters or 4 centimeters. But as they actually start to get used to the rotation, you notice, right, that they can actually start to adapt to it, right? And this, of course, involves the neocortex. So again, what they're doing is that when the rotation comes in, they're like, whoa, what's this? But then over time, over trials, right, you can see them be like, oh yeah, cool, I got this. And by about trial 60, so within 20 trials, you notice that their error starts to stabilize, even though it is actually slightly larger than the pre-rotation phase. And then what they do, just to be tricky, is at trial 41, they suddenly remove the rotation again, right? So people who are like, oh yeah, cool. I got this rotation. I got this. I can make these movements. I can change my motor behavior to compensate for this perturbation. Suddenly you see, whoa, perturbations in the other end, in the other way, right? And so now we've got these errors, probably at the same magnitude, 40 millimeters, but in the opposite direction, because they were expecting the rotation, right? Because that's what they've been trained in this rotation phase. But now it's suddenly gone. And so they're like, oh gosh, 40 millimeters in the opposite way. But they very, very quickly are able to recalibrate to the lack of rotation, right, which is the normal state. And you see that their endpoint error, boom, comes back to almost zero. And so this lovely work from Dizio and Lackner shows us a couple of things. It tells us that people can actually compensate for perturbations, right? And it tells us the shape of that kind of compensation or adaptation and how long we think it should take to occur. So in this case, based on this perturbation, about 20 trials, right? And of course, we can see that the transient initial perturbation actually causes large endpoint errors because we're just not expecting it. Okay, so this Dizio and Lackner study is really the seminal study upon which most of the rest of the work that we're going to talk about is based on. And so here's another study that Dizio and Lackner did where what they looked at here in the same study was not just the endpoint error shown up here, but they looked at the lateral endpoints, which we see here, which is basically, these are just bar graphs of what we're looking at, these little dots. And you see the curvature, which is the line. This is the curvature when we plot them in those kind of 4 phases. So this shows you over individuals, right? So it's just a different way to show you the information I showed you on the other page. But what we can see is, let's actually look at the movement trajectories, right? So the pre-rotation, you can't quite see it. It's this straight line is directly from here to here. Boom, straight line trajectory, right? Which is the first thing that happens. Now, when we add the rotation, let's have a look at those initial trials. So the first 20 trials, you can see that they actually make these rightward pushes because the perturbation is pushing them outwards here. And look at it. Their lateral endpoint is further away, right? They can't actually get to the target, which is why we see this this one here. It's about 2 centimeters away. And look at the curvature. The hand is really curved when it moves. But as you start to get used to the rotation again, right? These rotation final, we'll call it, those last 20 trials, you see that the individual is able to compensate and make those straight line reaching movements, which is why we see these pre-final coming back to the normal kind of level that we expect to see from their pre-rotation phase. And then, of course, because Dizio and Lackner are tricky, right? After people get used to it and they can make these straight line movements at about trial 80, at trial 81, what they do is they suddenly remove the perturbation. And what happens in the post-rotation? Look at it. They actually make these movements that are almost, complete mirror opposites of the rotation. And this is because they were expecting the rotation. And because they're expecting the rotation to push them right ways, they actually start to use more leftward movement, right? And so this is why this is coming like this. And here, what we can see again is that the endpoint error and lateral endpoint is a lot further away, so about 2 millimeters. And the curvature of the arm, whoosh, is a lot larger than in the pre-rotation and the rotation phase. And so these Coriolis force perturbations show us that we can actually adapt, right? We're adaptive mechanisms or adaptive beings, and that these actually occur via the cortex because of the length of time it takes. So when I was in Singapore, I was working in the Robotics Research Center, right, on this thing called the H-Man, which I've showed you before. When I got there, this is what the H-Man looked like. Pretty shitty, right? But here are the motors that, the encoders that can actually read what you're doing, and here's the hand. This is what the H-Man looks like now, and actually just last week, it came out for commercialization. And so what we did with the H-man was we looked at how people can actually adapt to forces using this manipulander. And so this H-man actually has active haptics because it drives it through the handle of which you're grasping, so it can push you forwards, it can push you in all of the directions, and also on the orthogonal, right? But also you can actually turn off the motors, right? And the person can actually make these movements by themselves without any help of the robot. And so in this study that we did, what we did was we actually produced a perturbation in the X dimension. So we were pushing them outwards, right? And what we did was this is the way we formulated the perturbation, because each perturbation is different depending upon the experiment. Not all perturbations are the same. So we derived a virtual Coriolis force field, F core, right, which was based upon P core, which we set to a constant level of 14.1 newtons per second, right? So this is 14.1 here, times the velocity in the y dimension, right? So again, what this means is that the faster the velocity you're moving, the more more force that's going to be applied, right? The slower you move in the y dimension, the less newtons that are going to be applied. Of course, remember, this is not an additive factor, it's a multiplicative. So it's not just 14.1 plus your velocity, it's times the velocity. The faster you go, the more the perturbation is going to push you. And then what we did was we looked at two conditions. We had a compliant channel and we had a stiff channel, okay? So what does that mean? So a stiff channel, what we did was we actually locked the horizontal degree of freedom, which only constrained participants to these forward, backwards movements, so in the y direction. So basically as though, there are actual channels on each side. That was what it would feel like. And then we had a compliant channel where we actually constrained the lateral movement to 200 newtons per second via elastic bands. So this actually allowed the person to get kind of some of that side-to-side movement, right? So the stiff channel, you can only make movement in the forward backwards, even though you feel the sideways force of the handle. The compliant channel actually gave you a little bit of give in the Y component, right? So you could move a little bit left and right. So using that same kind of paradigm as Diesel and Lachner, right, we had 4 phases. The baseline, where we just look at their normal behavior, right? And then we had the adaptation phase, where we actually put the perturbation on. But notice that we're splitting these into 2 phases, the initial and the later perturbation phase. We call it adaptation here. And then later on, starting at trial 150, we actually remove the perturbation completely and we see what happens. We tend to call this washout, just different names for things. So what you can see is that both in the stiff and the compliant channel, when you're just looking at baseline behavior, people make these very straight line movements, right? Perfect, great. What happens when we have the perturbation? You can see again that their hand gets pushed out because of the Coriolis force, but then after a certain time period, boom, they can actually correct and come back and reach the target. And same for the stiff channel, but look at the variability in the stiff channel, right? But then look what happens later in adaptation. In both of the conditions, you can see that they start to actually learn to adapt to the behavior, both with respect to their variability, so they become less variable, more consistent, if you will, and they don't get pushed out nearly as far, so they learn to anticipate the perturbation and correct for it. And then when we suddenly remove the perturbation, what happens? We get this washout. And the washout, what you can see, is almost a mirror of early adaptation. They're expecting to be pushed out to the right, and so of course they're applying more leftward force, but because there's no perturbation anymore, their movements actually end up moving to the left, and then they make these corrections back towards it, both in the compliant and the stiff channel. What's interesting to note though is that look at this consistency in the washout. People are less variable than they are in the stiff channel. And also look at the level of how far they're getting pushed left. Much greater in the stiff channel condition compared to the compliant channel condition. And so when we plot it on a trial by trial basis, what we can see here is that the adaptation is actually favored by a compliant channel, right? By allowing people to have this side-to-side movement, right? Allowing them to use their proprioception to guide their feedback responses. So what we can see here, sorry, it's a little small. Let me make it a bit bigger. Okay. So in the stiff channel, you can see, ooh, people are perfect. Great. Looking good, looking good. And then what happens is that when the perturbation comes in, they do very poorly, and then they start to come back and adapt. And when the perturbation is removed, they have poor performance, and then they come back to adaptation. But what's important to look at is the difference between the stiff channel and the compliant channel. Sorry, look at it this way to this way. So this is the amount of error that they have with respect to the target, how far away they are. So at the start of the perturbation, these people here in the stiff channel are about 60 centimeters away, and 60 pixels, sorry. And in this case, they're about there as well. But look at how quickly they actually adapt here. We can look at this red curve, which is how fast they adapt. And then look at the washout. See this? It takes them about 20 trials to come back in. And so this is a very different adaptation response to what we're seeing in the compliant channel, which is a lot shallower, right? In both down here. And what that means basically is that the compliant channel enhances the amount of proprioceptive information that an individual can use to correct their movements. And this helps them learn the dynamics of the environment that they're acting in, and the dynamics, of course, being that Coriolis field. And it allows you to adapt quicker. So think about this from a rehabilitation perspective. If you've got an individual, right, who is learning to use their arm again, you don't want to constrain their movements to a single plane. You want to allow them a little bit more of the degrees of freedom, if you will, right? Because that allows them to use not just their visual information, but also their proprioceptive information to feed back into this optimal feedback loop, right? So it allows them to use more sensory feedback than they would in the stiff channel. That allows them to make more appropriate and closer estimations that guide their motor commands. So I know that stuff is some pretty hard work, especially with the Coriolis fields. We're going to stop for a moment, and because we're at 42 minutes, and come back with some more perturbations in grasp posture. I'll share with you one of my studies, and then we will move on to some perturbations of the lower limb. And then, of course, what happens in cases of neurological disorders, such as stroke and Parkinson's and things like this. I hope you enjoyed it. Please let me know if you have any questions. This is my jam. I love it. I find it so exciting, and I hope you do too. Ciao for now.